Okay, I guess let's get started with our final day. Thank you everyone for coming back today. So for our final session, we are going to have the verification session. So first up, we have Roberto Rigamonti from HEIG-VD, who is going to be talking about Python-based flexible test benches for spacecraft payloads. So Roberto holds a master's in computer engineering from Politecnico di Milano and a PhD in computer vision from EPFL. And since 2014, he has been working as an embedded software engineer at the Institute for Configurable and Embedded Digital Systems of the Haute École d'Ingénierie de Gestion du Canton de Vaud. And there he is developing radio and FPGA-based systems for diverse applications, including space and search and rescue operations. Thank you, Roberto. The floor is yours.
Thank you for the introduction and good morning. So I'm going to present you a Python-based flexible test bench for a spacecraft payload. And this is joint work with my colleagues Enrico and Alberto. Before delving into the test bench, I'm going to spend a couple of words on the context. So this is an ESA mission, which is called Comet Intersector. And the goal is to explore a comet coming from very far away from the solar system. So the idea is to launch the spacecraft, park it somewhere in orbit. Guess it's easier than Geneva. And you leave it there. And once they find a comet that say, oh, this is interesting, they send the spacecraft, and the spacecraft does all the scientific stuff. And for doing that, they have 10 instruments on board. And I'm going to talk about this one, which is the Comet camera. And it's a high-definition camera on the main payload. And this is what the instrument looks like. You have a big telescope. And on the bottom of it, you have this one, which is a filter wheel, where you have 4 optical filters, which are used to set the telescope to the desired wavelength. And then you have also some heaters, because you have to keep the instrument at the proper operating temperature. So the tasks are to control the motor, which is below this filter wheel, in order to make it turn, and to control the heater of the instrument. And we plan to do that using a ProASIC 3 FPGA. The first thing we did was to outsource the development of this part to do things properly, like someone does the implementation, someone else does the testing, and we kept the job of verifying and validating the implementation. And there are some issues because, first of all, we cannot rely purely on simulation because the toolchain is not certified. Also, we found several bugs in it. And it's also important to test also the prototype board that we have. The biggest one is that in space development, the golden standard is the V model. And I would love that things work this way, but it's not. It's more like not this nice V-shaped thing. It's more like, I don't know, a spaghetti bowl. And so I would love to believe that the V model works as expected. So what were our strategies to face this task? So we started from a CocoDB-based Python test bench. And we know that things were going to change. From the first weeks, we knew that the requirements were going to change. So we made it as configurable as possible with JSON file placed everywhere telling, oh, you're getting the telemetry in this shape. And also, we wanted to be very paranoid. So check everything all the time. When you create a normal test bench, you say, OK, those are my input signals, and I expect these output signals. So turn on the motor. OK, the motor has to do this. But OK, I'm a bit paranoid. So what if when I turn on the heater, the motor starts moving too? So I want to check everything all the time. And it would be nice if we had a reusable framework for future projects. Before we did all the validation part using standard or HDL test benches, we wanted to get into this CocoDB stuff. Also, another thing is that one of the most time-consuming tasks is to come up with test scenarios. Here you have tons of things that you have to configure, and they vary according to the actual state of the system. So once you come up with a test scenario, you want to reuse it as much as possible. And you want also to do some randomization. But OK, we can use randomized test generator, but the requirements are going to change basically every week. So we had to modify each test generator to re-implement the model because things have changed in the meantime. That would be a lot of work. So, and last thing, we have to test on software, in simulation, and on hardware. But what if we could use one test bench, one set of test scenarios, and test everything in all situations? This is what the simulative test bench looks like. So here we have either a test engineer or a test generator, which creates a JSON file, which is just a list of at time t1, move the motor, at time t2, simulate a triggering of an Hall effect sensor. And this is fed into the drivers. The whole framework is a publish-subscriber framework. So the drivers on one side drive via CocoTB the HDL test bench. On the other, they publish to the whole test bench a message saying, oh, I've triggered Hall effect sensor 4. Below, we have, between the subscriber, we have the simulated components. So there will be, for example, a motor, which has encoded some invariants saying, whenever you see Hall effect sensor 4 triggering, you know that you have to do an emergency stop because you're going to crash on the side. So when the driver publishes, I've seen Hall effect sensor 4, the motor components instantiates a checker saying, now watch around, you know that you have to get an emergency stop. On the other side of CocoTB, you have the monitors, which observe what the HDL design is doing, and they also publish what they see on the other side. They say, OK, I'm seeing, I don't know, an heater turning on or a motor doing an emergency stop. And they publish this information, and the checker are listening, and they say, OK, the motor monitor said, I've seen an emergency stop. I was waiting for that. Cool. Everything is going fine. And the cool thing is that the hardware test bench is basically the same picture. I've just replaced this block saying, oh, here we have hardware test harness to connect all the tons of wires we have around. And then we have the hardware board. So if we focus on this part, we can explode it in this way. So we have the drivers that are saying what we have to play. And everything is here. I have a component which is called activity scheduler, which basically gets all the information from the drivers and creates a long list of long to-do list at time t1 do this, at time t2 do that, and sends this list all at once to a Raspberry Pi 4 via the Ethernet port. And the Raspberry Pi 4, here we have a real-time software which drives this interfacing board on the side, which in turn drives the prototype board. And all the outputs from the prototype boards are fed again into the interfacing board and are collected by, again, the real-time software running on the Raspberry Pi, which sends at the end of each test run to the main test bench, where we have some activity observers, which just write down and sort all the events that occurred in the meantime, saying, OK, I've seen at time t10 the motor turning on. And this is, at that point, again, publishing the information. They say, I've seen at that moment this thing, the time evolves. I've seen at that moment the other thing. So the rest of the test bench stays identical. This is just to show you what the hardware setup looks like. There are tons of wires everywhere, but that's it. And as I said, everything is based on invariant checkers. So they ensure that the requirements are satisfied all the time. Whatever we are going to do in the test, all the rest of the system is checked. For example, we have a component for the LVDS telemetry that gets the information, decodes the information. A monitor publishes that information, and a checker that is waiting for that information to verify whether there is compliance between the actual motor state and the telemetry information that we're getting can do that. We also have to assert some properties, because we have to say, I need this thing to be true in n nanoseconds. The trivial approach to do that would be, OK, you spawn a checker, you wait n nanoseconds, and then you say, if the thing is not came true in that time, there's an error. But we have some complex conditions to verify. For example, telemetry messages are not all the same. We have kind of 9 different types. So the information that I'm looking for might be in 8 telemetry frames. And that frame might be corrupted. So if I want to verify that within 2 telemetry frames the information is correct, I have to handle all these possibilities. I have to wait for 9, I have to wait for 7, then that frame is not correct, so I have to wait for another 9. So it's quite complex. To handle that, we created the 2 registries. So one is for time-based checkers, saying in that time I want this to be true. And the other one is for telemetry-based checks. That is, I have to check that within that amount of telemetry frames, the property to be true. And this is how it works. You have a driver that sets a value in the HDL design and sets also this value, publishing it to the simulated component. As a reaction, suppose that you have signal B that changes. The simulated components instantiate a checker which goes in the registry, and here says, I know that something is going to happen soon. And the registry, what it does is periodically reevaluates and looks if any of the checkers has expired. If so, then trigger an error. The monitor looks at the HDL design and publishes all the events that occur. And if the event is unexpected, that's an error. I mean, I turn on the heater and the motor starts moving, that's a problem. If it was expected, then goes in the registry, says, oh, this checker, it's fine, the event is occurred, so I can delete the thing. Otherwise, you have the registry which says, OK, this thing has expired, so trigger an error. We also automated test reporting. So we have a JSON description of the system, JSON description of the test. We feed the 2 in the test bench, and we get a test outcome as a JSON saying, this test has passed. Moreover, we have a JSON description of the test case, a LaTeX description giving more information, some nice screenshot of the oscilloscope and other stuff. And then we have the requirements, which is a big Excel file that they gave us. All of this goes into a Python report generator, which creates magically this PDF with all these tables saying that those are the requirements covered by this test case. This is the description of the test, what I'm going to do. And those are the results of my simulation. What future improvements can we add to this system? Thus far is open loop. So, for example, on the hardware, we send all the commands that we want to operate, saying at this time do that and do that. And then we get, at the end of the run, all the outputs. If there's an error in the transmission of a telecommand, too bad. Everything is going to start screaming that there are errors, even though maybe everything was fine. And we could have added more configurability. But what are the lessons learned? This is the most important slide. It's good to have a split in the development and test team, but if, like in our situation, you have very weak requirements, which change basically every week for 2 years in a row, and you have this split, you're going to face conflicts and time waste, because everyone is going to say, oh, no, I've interpreted it this way and implements that way, and the other team does the other way. It's very important to do human forecasting. This is a term I've borrowed from the risk management domain. So when you want things to move, since you have weak requirements, you cannot really say, do that this way because it makes sense, because people might have a kind of resistance to that. So you might forecast what the expected reaction could be and find the path of least resistance, saying, OK, maybe we can do that, that's going to work better. It's very handy to have semi-automated reporting, because when you're close to the project end, you don't have budget anymore. You have tons of reports to write, and that's very handy to press a button and get everything out. Never, ever make an assumption based on common sense, because other people might have a different common sense with respect to you. So it's like kind of be a bureaucrat and write the test bench only on what's written and not written in the requirements. And concerning the reusability, okay, this was a good proof of concept for the techniques and the tooling, and it has become now our go-to approach for design validation. And the exact code, well, cannot be reused in another project, but the idea, the thing that we've implemented, they can still be used, knowing that there could be breaking changes in the libraries, like, for example, moving to CocoaDB 2 in a few months. So that's it, if you have any question.
Thank you. So, any hands? Yes, please.
You did talk about invariant checkers.
Yep.
What do you mean exactly by invariant checkers?
I embed into I have a class representing a given component, like the motor, and inside it I have a set of properties which are said, like whenever you turn on the motor, you have to see the PWM moving within 10 milliseconds, for example. And so this is an invariant. Until the thing do not change, the motor has to be on. So this is a property that has to be there, and I don't touch it, so the PWM still have to be on.
So maybe I have a question.
Yep.
You say the code can be inspiration for future projects. Is this code available somewhere? Can we look at it?
Unfortunately not, because it's for the customer. But as I said, the code itself is not that usable. You cannot take it and put it in your project. But it's really this idea of having the checkers, the registries, stating when those events occur, you do that, and which were the most useful part of it. And really seeing that it's very effective as a way of creating a test bench using CocoaDB and Python, combining the power of the two.
Yes, go ahead.
Hi. Do you simulate your whole design?
Yeah. It takes a lot of time. And that's why we had to, it was useful to have this, the same test bench for all both the hardware and software part, because there were, for example, we have timeout, which take 2 seconds to occur. And so we were able to shorten the time by some tricks, but in that case, we were modifying the test that we were doing. Otherwise, we had to wait 2 seconds. And in simulation, it was like 12, 13 hours. So we cannot do that.
And how do you deal with proprietary IPs in CocoaDB? Is that fully supported?
In this design, there were no proprietary IPs. So everything was developed from scratch, because otherwise you have to, for ESA, you have to justify why you use that specific IP, and you have to give some guarantees about that IP. So it was easier to do everything by ourselves.
Okay, thanks.
Welcome.
Yes, go ahead.
So if your simulator supports the proprietary IPs, then CocoaDB has no problem with it, because CocoaDB only works on the interface side, and you usually don't have to look into the proprietary IP. So there shouldn't be a problem there.
Thank you.
Hi, I have a question regarding UVVM, because I understand, I think UVVM is also working with ESA. And was there any idea to use UVVM? And they also have some kind of requirements checker we saw yesterday. So that seems very useful. I think also that you encoded in JSON, automate the report generation.
Yeah, we didn't consider that because, I mean, with CocoaDB you have PyUVM, which could help in that part, but at the beginning the project seemed like very simple, very straightforward at the beginning, and then we discovered all the subtleties. I mean, the idea was in 2 weeks have all the requirements and then start something very simple, and then the spaghetti bowl exploded and englobated everything. And it became, now redoing that, I would probably use something like UVM and do something properly. But at the beginning, it seemed like an overkill, saying, oh, that's too much. So just doing something configurable, but not much past that.
Okay, thanks. It's maybe not too late for future to kind of try to find the common paths, because it seems there's many similarities.
Yep, yeah. That's a good advice.
Cool, thanks.
It's maybe harder than to play with the real board. So Python was a nice try for this, I guess.
Okay, any more questions? All right, then let's thank our speaker again.
Thank you.